We have been looking at density matrices as it is one of the most important aspects that helps us in implementing quantum computing and quantum information processing. And in the first lecture of this week, we have looked at some of the basic fundamentals of density matrices, which have been implicitly used by us, but it was important for us to start off on this area to make sure that the understanding is complete in this field. So, on going forward, we want to just ensure that we are in this topic of density matrix, where we are using reversibly the terminology of density operator as the same as density matrix, and we are looking at statistical ensemble, where the quantum subsystem is being treated with some probability of the wave functions that essentially create the subsystem, quantum subsystem, and this is a very fundamental point of view, as it enables us to understand the system even though we have difficulty in gaining information about it. So, in some sense, for pure states, we know that we can find out the expectation value of the system by applying. It helps us to know about the system even though we have very little knowledge about the system. So, going ahead with this principle of the density matrices, here are some of the examples that we have been starting to look at. The density matrix of mixed state can be written as a sum total of the inner product and the probability of observing that particular state. From previous lecture, we have a few examples that we had looked at. A superposition of two states, whether they have a phase factor, would give rise to the same density matrix. So, whether it is ket 0 plus ket 1 or ket minus 0 minus ket 1, both of them will have the same density matrix. Similarly, with ket 0 and ket 1 with probability half, ket 0 and ket 1 with probability half, superposition of ket 0 and 1 with probability half, superposition when the mutual sign is minus with probability half, versus a superposition of ket 0, ket 1, 0 plus 1 and 0 minus 1, each of probability quarter, will all have the same density matrix half 1 0. So, given this definition, when we look at these different density matrices, we realize that the properties of these two are indistinguishable as far as the density matrix is concerned. Similarly, the properties of all these sets, combinations where all of them could occur, having a total density matrix which can be given rise as a result of any of these three combinations, 3, 4 and 6, will all have the same density matrix. However, when they all have the same density matrices, they cannot be having distinguishable property in terms of density matrices. So, all the properties associated with density matrices would only work on the row, and as such all the three cases 3, 4 and 6 will behave similarly. Again, a case where we have ket 0 with probability half and ket 0 and 1 with probability half would have a density matrix which would be given by rho half this plus rho half of each of them half up, which give rise to a total density matrix of this kind. Now all these individual density matrices, say and this particular density matrix, they are all distinct and they will all be possible to be distinguished, and similarly they can all be looked at independently and they will have different values. We can also have another way of looking at density matrices. For example, if we have a combination where we have a state which is mix of two different superpositions states, and in that case if we are measuring one of the qubits, say we measure the first qubit of this combination, then the first qubit of probabilities which will be 0 will be coming only from here, and first qubit of this which will be having a probability of 1 will only come from this contribution. So, they will have distinct contributions. We have actually dealt with these kinds of cases earlier when we were discussing the aspects of implementation and developing the principle of quantum information and computing. So, they all are very relevant, and it is important to note that in most cases the information of anything which is not pure can only be determined when we are looking at the density matrices. So, there are three properties of density matrices which are important, which is that trace of rho is going to be 1 always, which means that it is a normalized case, and that is because the trace of the density matrix is essentially the total probability of the system. So, it is a sum total of the diagonal elements. It is the density matrix is going to be Hermitian always. The projection of the density matrix along any of the composite states will always be either 0 or more than 1, essentially stating that the projection of the density operator, any of the states that constitute the density matrix, is either going to be 0 or more than 0, as that they represent the probability of the occurrence of or the weightage factor of the contributing state. Moreover, for any density matrix rho satisfying the above properties, there exists a probabilistic mixture whose density matrix is rho. So, we can use density matrices and trace to calculate the probability of obtaining state in measurement. So, if we perform a von Neumann measurement of the state rho with respect to a basis containing ket phi, the probability of obtaining ket phi is given by bracket of psi rho square, which is the probability, and that happens to be the trace of rho times inner product of phi. Now, this is for a pure state. This is the definition for a pure state. Question could be how it would be for a mixed state, and as we have discussed in the last class, it will be the same. So, this we have looked at in the last class. This is just to remind you that essentially it is the same thing. So, if we use the density matrix and trace to calculate the probability of obtaining the state in the measurement, which is basically for making the measurement for a mixed state, it will be the same. It will always get the same state. So, if we perform a von Neumann measurement of the state with respect to the basis containing phi ket, the probability of obtaining the phi ket is going to be given by the same probability, which is the outer product square times its weightage, and we can get the trace reduced to the same function, same form as we had for the pure state, which means that this is one of the biggest achievements of density matrix, that it enables us to look at mixed state in the same mixed state and provide information which is otherwise so difficult to get. Conclusions that we have achieved as a result of discussions that we did in the last lecture and now is that the density matrix has the complete information. In other words, the density matrix contains the information necessary to compute the probability of any outcome in any future experiments. So, spectral decomposition can be used to represent a useful form of the density matrix. Often it is convenient to rewrite the density matrix as a mixture of eigenvectors. Eigenvectors with distinct eigenvalues are orthonormal. That is one of the fundamental requirements of quantum mechanics. For the subspace of eigenvectors with a common eigenvalue, which are degeneracies, we can select an orthonormal basis. We can, in other words, we can always diagonalize the density matrix so that it is written in terms of this form, where phi k ket is the eigenvector with eigenvalues p of p k, and phi k set forms an orthonormal basis. So, this is basically the definition of density matrix which we have been following. It is a very useful definition because this is one of the ways to get information of states which are otherwise not possible, as we have been discussing. So, we have been using the notation of the matrix notation as well as the vector notations interchangeably. So, it is important to have a small review of the product notations here. So, this is an outer product notation where we show how the wave function psi ket and phi ket, which are vectors, and if we define a linear operation matrix by this form, which is more commonly also known as the outer product notation, then we get this particular form where we have where we can write it out, and in the simplest form we can essentially get a projection or get the contribution of the particular state in the superposition, and this can be connected to the matrices by utilizing the fact that these are connected by using their coefficients, and that can be written in this kind of a form, bra versus the ket forming the row versus the column matrices. So, the row is the ket and the bra is the column, and by utilizing these principles we can actually write out that the outer product of two vectors A and B is simply the multiplication of a column matrix with a row matrix. The bra being the row matrix, which is the, and ket being the column matrix, and the bra being the one which is a complex conjugate notation. So, when we use this outer product notation, we are able to get these different examples where we can see that the 0 0 is a diagonal matrix of 1 0 versus 1 1 is a diagonal matrix of 0 1, and we can have operations which would essentially mean the gate. So, for instance, is Z gate is nothing but an operation where we have the outer product 0 0 of and minus of outer product 1 1 would give rise to the J gate. The outer product of 0 and 1 would give rise to the off diagonal element, and similarly the one with 1 and 0 would give the other off diagonal element, and that way we can also have the X gate, which can be the superposition of the 0 1 and 1 0. So, the X gate could be the superposition of 0 1 and 1 0 inner products. One of the advantages of the outer product notation is that it provides a convenient tool with which to describe the projectors and thus the quantum measurements. So, if we recall that the projector P onto space E1 E2 acts as the P applied on to alpha E1 plus beta E2 plus gamma E3, it will be essentially alpha E1 and beta E2. This gives a simple explicit formula for P, since we know that a outer product form of the two would give rise to E1 E1 and E2 E2 coming together in the outer product form. A superposition of that would give rise to the projection operator. More generally, the projector onto a subspace spanned by the orthonormal vectors is given by this projector, which is generally the outer product of the two vectors Ej and Ej summed over all of them. We should also revise the ensemble point of view in this particular context, which can be looked at in this way. Once we imagine a quantum system in the state psi of j with probability p of j, we can do a measurement which is described by projectors p of k. The probability of the outcome of k being in state psi j can be written in terms of this particular form, where the probability of k times state psi of j p j, the probability of being in that state p j, can be written in this particular form. So, this is in terms of the projectors. So, that can be rewritten in terms of the trace of the property, and then we have the very important aspect where we have the trace rho times the projector p k, where rho is again as p j psi in outer product of psi j's, and this is the density matrix. So, rho completely determines all measurement statistics. So, that is one of the reasons, once again, the measurement statistics is so important and so understanding when we do ensemble measurements, because rho basically gives rise to all the results that we are interested in. So, this is a highlighting result, and so this is something which should be remembered. So, let us now connect it to the qubit case. So, we can calculate the density matrix in this form. Suppose we say that the pure state of psi is 0 with the full probability, then our probability density matrix is outer product of zeros, which give rise to this particular density matrix. If we have the wave function representing the pure state 1, then we have the other case where it is rho 1. So, if we have the wave function which is a combination of say 0 and I of 1 with over root 2 with probability of 1, then the rho would be a conjugate of these two times where we change the bras and the kets, we get the negative sign. Then we will be having a density matrix which will look like this. So, density matrix is a generalization of state, and it can be looked at for any particular state that we are looking at. So, we can calculate density matrix irrespective of how the particular state looks like. Pure states as well as states which have different contributions all give rise to values which can be represented by density matrices. Now, if we let the probability of measuring the pure state 0 with p and pure state 1 with probability 1 minus p, then we can find that the density matrix would be represented in terms of the probabilities of these two, and the trace has to be 1. So, the probability of state 0 is along the diagonals with p and 1 minus p. So, the measurement in the 0 1 basis leads to the probability which can be looked at with respect to this, and so the probability of 0 simply is the trace of rho with respect to the outer product of the 0 states, and we get correctly the value as p as our probability, and similarly when we do the same with for 1 we get 1 minus p as expected. So, the advantage, as I have been mentioning, is the simplicity of the overall process. The quantum states which are mixed, that can be looked at as a result of density matrix notation. If we have an arbitrary sum of states which are with all these probabilities, as long as the sum of these probabilities has to be 1, as we know, we can have a condition where we can set them up and we can write out the density matrix. We know that the probabilities of the states, and we want to find or check the density matrix, we can always write it down with each of the probabilities for each of them to find out the density matrix, and as long as it is only 2 states involved, it will be a 2 by 2 density matrix, and so on and so forth. So, we can also look at the dynamics of the density matrix. If we have a quantum state in state psi j with probability p j, the quantum system undergoes the dynamics described by the unitary matrix U. The quantum system is now in the state U psi j with probability p j. The initial density matrix is, as we had discussed, p j psi j outer product. The final density matrix is rho prime with an unitary operator applying on both sides, and so it, since the unitary operation is commutative, it will come out and we can get back to this form which gives rise to the operator, the unitary operator acting on the rho to give rise to the final result. So, the dynamics of the density matrix can be calculated, new density matrix from the old density matrix and unitary evolution of the matrix. This is analogous to calculating a new state from an old state and unitary evolution matrix U. This new formalism is more powerful since it also refers to mixed states, and that is the biggest advantage of the density matrix. And so, whenever this particular operation is being done, it can be looked at for any particular state. Let us take a single qubit example where we calculate new density matrix by operating with an inverter on old density matrix. Say you have the pure state 0 with probability p and state 1 with probability 1 minus p, then our density matrix will be p 1 minus p 0 0, as we have discussed. If there is an x gate is applied, then rho prime will be x rho x dagger essentially, and that will be equivalent to this. Now, if wave function is 0 and 1 with equal probabilities, then rho is equal to I over 2, which is a completely mixed state, and if you have any unitary operation U is mixed, unitary gate U is applied, then rho prime will again give rise to the I over 2 values. So, what class of matrices correspond to possible density matrix? Suppose we have rho equal to probability times the outer product of psi j and psi j is a density matrix, then the trace of the density matrix should be equivalent to equal to 1. The trace of the density matrix is 1. So, for any vector A, as long as we can write the density matrix in such a way that its trace is 1 and any projection of that is going to be greater than 0, then it will be current. Summary is that the trace is going to be 1 and rho is a positive matrix, then we can consider that to be a density matrix. So, to consider any matrix to be a density matrix, this is the first two properties that are necessary to be seen. So, in summary, the ensemble point of view that we are looking at it has the definition of density matrix for a subsystem, for a system with state psi j with probability p j, which is given by density matrix, which is the outer product of the psi states with probability p j. The dynamics can be seen as any unitary operation can be utilized to see the new state. A measurement can be described by projectors pk which give result k with probability trace of pk rho, and the post measurement density is rho of k prime, which is pk rho pk over trace of pk rho pk, and it can be characterized with the fact that trace rho equal to 1 and rho is a positive matrix. Conversely, given any matrix satisfying these properties, there exists a set of states psi j ket and probabilities pj such that rho is equal to summation over j pj outer product of psi j's. So, in this regard what we have been discussing is a very important property of these normal matrices also, which have been implicit, which is that in matrix is normal if you can have, if it is commutative. So the concept is if there exists a unitary U such that the diagonal such that there is a matrix M which can be reached by using a unitary operator through a diagonal matrix, that is a unitary diagonalizable, then the matrix M is normal. So, examples of abnormal matrices is, for example, this particular simple matrix 1 1 0 1, which is not even diagonalizable, and the other which is 1 1 0 2, which is diagonalizable but not unitary. So, these are the kinds of abnormal matrices, but generally matrices are normal, which is what we use if this is satisfied and if they are unitarily diagonalizable. So, these two properties are to be satisfied for having normal matrices. Eigenvectors and eigenfunctions always utilize normal matrices. So, for unitary and Hermitian matrices, we have normal matrices with respect to some orthonormal basis. They are unitary, which implies that lambda k square is equal to 1 for all the diagonal square of all of them are equal to 1 for k, all k. It is Hermitian, which means implies that it is a the diagonal elements are all real for all k, and there are certain matrices which are both unitary and Hermitian, for example reflections, where the diagonal elements are essentially +1 and -1 for all k's, and so that is the way how things are. Now, there are these positive semi definite matrices also, which have been often used in these kinds of studies in terms of gates and application for the quantum mechanical operations. So, positive semi definite means that they are Hermitian with the diagonal values of greater than 0 for all k's. There exists a theorem where the normal matrix is positive, normal matrix M is positive semi definite if the normal matrix is Hermitian, and for all values of ket phi they will be positive. So, positive definite means that the eigenvalues will be greater than 0 for all k. And one other very important thing which we have always used are the projectors and density matrices. As we have been saying, the projectors are Hermitians and the square of them are equivalent to the same, which means that, which implies that M is a positive semi definite and the eigenvalues are lies within 0 and 1 for all k. The density matrix itself is a positive semi definite and trace as its trace of the matrix is 1. So, as we know this, and with both projectors and definite matrices, for example rank 1 projectors where the eigenvalues are 1 if k equal to 0 and it is equal to 0 if k equal to k is not equal to 0. So, these are basically the diagonal matrices. So, in some sense the concepts of the matrices, the nomenclature of matrices that we have been using are of the kind where most of the matrices we use for quantum mechanical terms are normal and they are if Hermitian then normal, then that is a Hermitian one. Then there are these reflections which can be unitary and it can lead to normal matrices, and there are these rank 1 projectors which can give rise to density matrices, projectors, and the positive semi-definite. The other very important part which we should refresh is the Bloch sphere for qubits, which we have gone through several times, but it is also another place where the density matrix representation can make a big difference. So, if we consider a set of all 2 by 2 matrices of rho, then they have a nice representation in terms of Pauli's matrices that we know it, and those are the few Pauli matrices which are the gates that have been used all the time. Sigma x or x gate, which has all the diagonals as 0 and the off diagonals as 1. The Z gate, they call it, which is basically the sigma Z, the diagonals are 0, 1 and minus 1 with off diagonals 0, and sigma Y is the Y gate, which has diagonals as zeros and off diagonals as complex conjugate of I. These matrices combined with the identity forms a basis for the vector space of all 2 by 2 matrices, and that is why these are very important, and we can express density matrices rho in this basis. Note that the coefficients I is half, since x, y, z have trace 0. So, all the value of the trace from diagonal is supposed to be 1, will have to come from I. So, we can express the density matrix rho for a Bloch sphere of qubits along this form. Rho is equal to half with the coefficient C x, C y, C z for x, y, z with I. Let us consider the case of pure state psi, where without any loss of generality, psi is equal to cosine theta 0 state times to the power I phi sin theta I. So, all these theta and phi are real elements. If we consider that, then we have a density matrix which looks like this form, which is possible to equivalently write in this form. Therefore, we can get the coefficients C z, C x and C y equivalently in between these two forms. These are the polar coordinates of the unit vector C x, C y, C z, which is in the real form. The Bloch sphere for qubits, location of pure and mixed states can be looked at also in this sense. So, in the Bloch sphere, we know that we have a 0 and 1 along the axis, and we have these different notations where we can have the superposition of these states. The orthogonal corresponds to the antipodal here, and the pure states are on the surface and the mixed states are inside, being weighted average of the pure states. So, this is how it can be looked at. So, the mixed states are the ones which are inside the sphere, as we show by the red line, all the parts of it, whereas the pure state are always on the surface of the sphere. And most of the time when we essentially describe in initial terms how the Bloch sphere is and talk about the discussions about the vector motion and everything, it is always with respect to the idea that the vector is pointing on or moving, the state is always on the surface of the sphere, which is what not true in case of the mixed state, as they are being weighted by average of the pure states. I think we have covered enough of these concepts where we have linked all the different aspects of the states that we have been and the gates that we have been using in the terminology of the density matrices. In the next lecture, we will be actually utilizing all these terminologies and the connections that we have established in this class to see how measurements and the understanding that have been utilized in terms of the implementation are much more easily understood in terms of density matrices. See you in the next class.